Good day everyone. In this video, I'll be introducing our self-balancing robot project and explaining how we assemble the robot step by step. A self-balancing robot is a two-wheeled robot that can stand upright on its own by constantly correcting its position. It works using sensors, motors, and a controller that continuously checks if the robot is leaning forward or backward. Once it detects movement, the motors immediately respond to keep the robot balanced. This type of project is commonly used in robotics and control systems because it combines programming, electronics, sensors, and mechanical design into one system. It also helps us understand how feedback systems work in real-life applications. Before starting the assembly, let's first take a look at the main components used in this project. First is the Arduino Uno, which serves as the brain of the robot. It processes the data coming from the sensor and controls the motors. Next is the MPU6050 sensor, which acts as both a gyroscope and accelerometer. This sensor detects the tilt and movement of the robot. We also have the L298 motor driver, which controls the motors since the Arduino alone cannot provide enough current to run them directly. Of course, we also need the geared DC motors, wheels, battery pack, jumper wires, and the robot chassis. Now let's proceed with the assembly. The first thing we did was attach the two DC motors on the chassis. We made sure both motors were aligned properly because uneven placement can affect the robot's balance later on. After securing the motors, the wheels were attached tightly to the motor's shafts. Next, we installed the battery pack onto the lower part of the chassis. The battery placement is important because it affects the center of gravity of the robot. Keeping the heavier components lower helps the improvement and stability while balancing. After that, we mounted the L298 motor driver near the motor so that the motor wires would be shorter and more organized. Then, the Arduino Uno was placed above the motor driver using screws and spacers. The MPU6050 sensor was then attached carefully near the center of the robot. This part is very important because the sensor is responsible for reading the robot's angle and movement. If the sensor is loose or tilted incorrectly, the robot may not balance properly. Once the major components were installed, the organized jumper wires to prevent them from getting tangled with the wheels. Proper wire management also helps avoid loose connections during operation. At this point, the physical assembly of the robot was already complete. Even though the structure looks simple, each component has an important role in helping the robot balance itself. The basic idea behind the robot is actually very straightforward. When the robot starts leaning forward, the sensor detects the tilt and sends the data to the Arduino. The Arduino then calculates the correction and commands the motors to move forward. If the robot leans backward, the motors rotate in the opposite direction. This process happens continuously in just fractions of a second, allowing the robot to remain upright. Overall, the self-balancing robot requires proper positioning of the components, stable mounting, and organized wiring. A good mechanical setup makes it much easier for the robot to balance correctly later on. And that's the end of the introduction and assembly explanation of our self-balancing robot project. The wiring stage is very important because even one incorrect connection can prevent the robot from working properly. Since the robot relies on communication between the sensor, Arduino, motor driver, and motors, all connections must be checked carefully. The main components involved in the wiring are the Arduino Uno, MPU6050, sensor, L298 motor driver, DC motors, and the battery pack. Let's begin with the MPU6050 sensor connections. The MPU6050 communicates with the Arduino using I2C communication. The VCC pin of the sensor is connected to the 5V pin of the Arduino, while the ground pin is connected to the ground. The SDA pin is connected to A4 and the SCL pin is connected to A5. The interrupt pin or INT pin is connected to digital pin 2 of the Arduino. These connections allow the Arduino to receive tilt and movement data from the sensor in real time. Next is the wiring of the L298 motor driver. The motor driver is responsible for controlling the speed and direction of the motors. Since the Arduino cannot directly power the motors, the L298 acts as the bridge between the Arduino and the motors. For the control pins, IN2, IN1, and IN3, and also IN4 are connected to the digital pins of the Arduino. These pins determine the rotation of direction of each motor. The exact pin numbers may vary depending on the uploaded code, but the setup process is generally the same. The left motor is connected to the out1 and out2 terminal of the motor driver, while the right motor is connected to out3 and out4. For the power supply, the battery is packed and connected directly to the L298 motor driver. The positive terminal goes to the 12V input while the negative terminal goes to the ground. One very important thing to remember is that all components must share a common ground. The Arduino ground, motor driver ground, and battery ground should all be connected together. Without a common ground, the robot may experience communication problems or unstable behavior. After completing the connections, we carefully checked each wire to make sure nothing was loose or connected incorrectly. In projects like this, loose jumper wires are one of the most common causes of problems, especially when the motors start moving and creating vibrations. We also organized the wires properly to avoid interference with the wheels. Cleaner wiring not only looks better but also makes troubleshooting easier later on. Once the wiring was completed, the Arduino code was uploaded into the board. During operation, the MPU6050 continuously reads the tilt angle of the robot and sends the information to the Arduino. The Arduino processes the data and sends commands to the motor driver so the motors can react immediately and maintain balance. So basically, the entire wiring system allows the robot's components to communicate with each other and work as one complete balancing system. And that concludes the wiring explanation for our self-balancing robot project.
Oh. Amo. Ano ako man? Buwak.